Professor Casey Kong from University of Kansas. His specialization is theoretical particle physics. I think I remember, I recall looking back, he had implemented some new physics models into, I think he used CalCap or CompApp. And then I think he probably used LANHEP. So I think some of my students would find this very fascinating. And then recently Casey has been, studying dark matter. And today he's going to talk about particle physics in the computing frontier. I'll let you start.
Okay, yeah, thank you. Thank you for the introduction. I don't know, some of you might remember I visited Wichita State, I think about 5 or 6 years ago when Terrence joined the Wichita. He kindly invited me for a talk 5 or 6 years ago. That was a very nice trip. That was my first time to be in Wichita. Unfortunately, this time online, but it's very nice to see you all again. And then giving me opportunity to talk to you about what I have been doing for last a couple of years or so. Hope everyone's doing okay. Okay, so let me start. So this is the outline. So I will I will begin with a very brief introduction to the standard model. And I will talk about the Large Hadron Collider. And then I will discuss the main topic, how we use machine learning in the particle physics research. So I think since we have, I'm pretty sure that you have heard a lot of talks about the standard model LHC. So I will try to be brief, and then I will try to give a slightly different perspective instead of listing all details and then so on. So probably I should try to avoid that. So if things are unclear, please let me know, because the way I will be presenting will be kind of might be a little strange. Okay, and as usual, because this is online talk and there is always a time delay, there is a connection issue and so on. So please let me know. And somehow I cannot see your faces and so on. So just to speak up freely. Okay, so in case I don't finish my talk today, which is likely, and this is my final slide. And I just wanted to mention that particle physics theory and experiment provide actually a very fun playground for advanced mathematics and data analysis. It's actually a great application of the computer science in general. And then I should tell you that I'm a particle theorist, as Terrence said, and I'm not a machine learning expert. I'm just excited about the opportunity playing with the machine learning idea, quantum computing idea in general, but I should say I'm no expert. I'm just one of the users of this kind of new tools. I know there are experts in the audience, so if this is a kind of too straightforward for some of you who are already familiar with the, machine learning, please bear with me. Hopefully I can give you something different at the end. Well, so what are we trying to do? So in particle physics and broadly in generally in physics, after all, we like to understand how universe works. And in particle physics and nuclear physics, as you know, we are interested in the smaller scale, right? So to understand universe, we can start with the very large scale. We'll go back all the way to the very small scale, close to the beginning of the Big Bang. And then right now, the energy of the LHC is about the 13 tera electron volt, which corresponds to 10 to the minus the 18 meter or so. So that's the sort of the energy scale and the length scale we are probing. In terms of time, it's roughly 10 to the minus 10 seconds or so. So anything around that thing, LHC should have some sensitivity. And also, as we know, we are living in a very particular time because we know how big the universe is, but we do not actually have a clear idea what most of the universe is made of. We know dark matter exists, we know dark energy exists, but what are they? We do not know. So we still need to answer all these questions. How do they interact with themselves? How do they interact themselves? Do they interact with the standard model? Besides the gravitational interaction, how do we find them? Then is there only one kind? There are a lot of questions. Unfortunately, we know nothing about them except that their existence. Well, to understand, of course, the fundamental building blocks of the universe, I mean, we smash things and we look at the remnant of the debris of the collisions. And then we have found the atoms and the nucleus and the protons. And these are the things that we have been finding for past 100, 200 years or so. Now we know that currently electron and then quarks are known to be the fundamental particles. And then their current limit on their size about 10 to the minus 18 meter, which corresponds to 13 TeV collision energy of the LHC. So if these guys have internal structure, which is much smaller than 10 to the minus 18, 19 meter or so, LHC doesn't have a sensitivity yet. It might actually tell us some hints about the internal structure of this fundamental particle. Hopefully we can see something new. Now, again, all of you have seen this thing many, many times, so probably I will go fast. And this is the summary of the standard model. And here is the fermions and the gauge bosons. And these are the quarks, and these are the leptons, and the first generations, second generations, third generations, right? And then finally, Higgs was discovered about 10 years ago, 10 years ago, I guess, 9 years ago. And then these are the names of experiments which discovered these particles. So this is truly international collaborations. Now, what's interesting is these particles are classified as fermions and bosons, but there is a little bit better way to classify all these particles. So standard model particles, these fundamental particles are nothing but irreducible representation of the space-time symmetry, namely SO1, 3. And then I don't mean to explain every single details, but as you know, the particles are explained via wave function. This wave function carries, wave function is a function of space-time, but in addition to function of space-time, there are a lot of indices. So these indices kind of represent how complex this object might be. So depending on what kind of object we consider, the number of the indices will be slightly different. As you see, the Higgs carries only one additional index, which should be simplest guy among all. But the quarks carries at least 4 indices, whatever they are. So these guys are somewhat complicated. And the gauge bosons carries the 2 or 3 indices and so on. So all these guys makes a very complex Lagrangian or Hamiltonian system. Here is the full list of the standard model Lagrangian. And as you know, this is not solvable. So unfortunately, we have to rely on approximation method, for example, perturbation and so on. So we have to develop lots of method to be able to calculate certain things to certain precision. Of course, Professor Figge is one of the experts on this QCD calculations, trying to develop lots of method and then tools. I don't know how many undergraduate or beginning students are here. Maybe usually speakers are asked questions. Maybe this time I will ask undergraduate students this question. So if I ask you to solve this question, I mean, of course, this is obvious. I mean, we know that there are 2 solutions. But if you are going to ask the same question to students in elementary school, then probably some of them may not know about the concept of the square, right? Basically, the negative concept, negative number. They don't have a concept of negative numbers. Now, if you ask the same similar question, second question on the screen, and to the middle schoolers, they may not have a concept of imaginary numbers, right? I mean, we know the answer, of course. Now, I really like to ask undergraduate students whether you can solve the log of -1. Here, ln means the natural log, the mathematical symbol. How do you calculate the log of -1? Of course, the first very immediate answer is, well, log of a negative number is not defined. So you are violating the rules. So you cannot do that. You cannot calculate it. This doesn't make sense. Then next question is, sin x equal to 2, can you solve this equation? Well, sin x, we are told the sin x and trigonometric functions, especially sine and cosine, actually oscillate between plus minus 1. Sin x never reaches 2, so therefore there should be no solution. Well, I mean, this can be illustrated very easily, right, using the graph. It is a blue curve represent the log function, and the yellow-orange curve represents sine function. Here is a x equal to 2, right? So x equal to 2, and then the orange curve, which is sine, they do not meet. So therefore, there is no solution. And the log function is defined in the positive x value. So there's nothing in the left-hand side. So when we insert the -1, there is no solution. Well, let me look at this guy one more time. The x squared equal to -1. Here is an x squared equal to -1, moving 1 to the other side. So we are solving x squared plus 1 equal to 0 equation. So this guy is equal to 0. That's the second equation. So in the graphically, we see this the blue curve, right, quadratic. So we want to find the solution where this blue curve meets x-axis. But there is no intersection. They do not meet, of course, right? I mean, we know that already, but we know the solution is x equal to plus minus I. So what that tells us is that there is something else beyond. So if you look at this guy, actually the solution doesn't exist along the x direction. Solution exists in the different dimension. I mean, if you like, you can call it external dimension, but in addition to real axis, actual solution exists the imaginary axis. That's why we are not able to find the solution from the intersection of the two graphs, right? The x-axis and then y equal to x squared. Solution exists in different dimensions. Now, what I want to ask you is, let's imagine some number like this, x times y. And then I'm going to assume x and y are complex numbers. Then x times y should be equal to y times x. They commute. I mean, it's commutative. We know this. Now, what I'm going to do is I'm going to introduce some new numbers. So let's say alpha, beta, and alpha and beta are not 0. And then I'm going to introduce some property just by hand. And then when you flip the order of these two numbers, with this guy, pick up the negative sign. So alpha times beta equal to minus beta times alpha. Can you find such number which actually satisfies this anti-commuting property? This product is not the regular product, right? It's very weird product, because when you interchange the order of the two numbers in a product, they commute, commutative property. But suppose we invent some new number system, alpha and beta, and then has this anti-commuting property. Can you imagine what number this might be? First of all, it's not a matrix. Matrix is not a number. It's a collection of numbers. So I said this is a number. We don't know. But let me assume that maybe such a number system exists. And then let's say the big G is a set of such numbers, anti-commuting numbers. And we are going to assume this guy is not 0. I mean, if it's 0, it's a trivial, so it's not fun. So let's say this guy is not equal to 0, but belongs to this weird set. But then according to this property, if I multiply by the same number twice, basically alpha squared, but this guy needs to pick up the minus sign, right? Beta equal to alpha, then alpha times alpha equal to minus alpha times alpha. Therefore, alpha squared equal to minus alpha squared. Therefore, alpha squared equal to 0. Yet alpha is not equal to 0. So does this make sense? I mean, it doesn't make sense for now, right? Alpha squared equal to 0, that means alpha must be equal to 0. Now I'm going to change direction slightly. Now I'm going to assume this alpha is again big G, belongs to big G. And then I'm going to assume this A0, A1, all these A numbers and function F is a complex functions or real function, complex functions. So I'm going to consider some function whose value is a complex number, but which takes this number, weird number, as input. So I'm going to do Taylor expansion, right? We know this one very well. So the A0, A1 alpha, quadratic, and cubic. But if alpha satisfies the anti-commuting property, alpha squared equal to 0, so all the high order terms are 0. It's very nice, right? When we do Taylor expansion, we always worry about precision, how many terms we should keep. But in this case, expansion in terms of this kind of variable actually truncate exactly at the linear order because all high order terms are 0. This expansion is exact. Now, what I'm going to do is I'm going to consider another example where the psi is satisfied this property, but x and y are now real number. Now imagine that we are interested in the product of these two wave function psi, and then each one is defined at the two different locations, x and y. Now suppose this guy psi represents some property of electron, for example, and you bring the second particle closer to the first particle. So I'm interested in computing. Bring the second particle close to the first particle, right? Then what would be the value of this expression here in the bottom of the screen? Because psi satisfies the anti-commuting property. and the y gets closer to x. So that means this entire expression will be exactly the same as the other expression. Then since psi is anti-commuting, this guy must approach 0. So that's what we call the Pauli's exclusion principle. Although this is not really a mathematically rigorous proof, at least you can kind of get an idea how the Pauli's exclusion principle related to the mathematical object in this case. Such a number system is what is known as a Grassmann number. So Grassmann number is a classical number, the anti-commuting number. And since now we have a new number system, remember how we studied all the mathematics? We started the real number, complex number, and we started the calculus integration derivative in the one-dimensional case, generalized to the multi-dimensions. And then now we do the same thing in the complex variables. And then remember, we can make it even more complicated, generalizing to the functional integrals. Now we have a completely new number system. We have to learn calculus one more time. But believe it or not, in this case, actually doing an integration is the same as taking the derivative because there is no inverse. Because of this anti-commuting property, calculus is also very weird. And in this case, doing a derivative is the same as doing an integral. So that's a very interesting thing. And I'm not really expert on the stock markets, but I was told that the Grassmann number and the path integral is actually has a great application in predicting the stock markets. So maybe I'm interested in actually going back to some of the articles, how the Grassmann number and the path integral is used in the prediction of the stock market. So actually, personally, what I'm interested in is how are these Grassmann numbers can be realized on the neural network computer system? Because in the computer science, there is no concept of Grassmann number. But believe it or not, Grassmann number is one of the fundamental number system that we have in physics. So what's peculiar about the Grassmann number? Because half of this standard model particles, namely fermions, are actually Grassmann numbers. Isn't that weird? Because here's a gauge boson, right? Glue, photon, and Z and W particle in Higgs boson. So roughly half of these guys are regular numbers. But the other half, which is a fermion, quarks and leptons. Quarks and leptons are described by Grassmann numbers. Why? We just saw that the Grassmann number has a very weird property. You square it, you get 0. And of course, we learned these things from the Pauli exclusion principle. But in terms of numbers, these guys are very weird numbers. If you square it, you get 0. Why? I think this is a great mystery mathematically. In the why nature, namely fermionic particles in nature, these guys are described by Grassmann number. The other guys are described by the regular numbers. I think this is, once again, if you think about it, we don't know the answer. That's the way nature is made. And another peculiar thing about the fermions, actually fermions are spinors. And then probably you hear a lot about the spinors and spins. And a lot of people think the spin is a quantum mechanical quantity. But believe it or not, it's a good spin concept is completely the classical quantity. And then unfortunately, we learned this spin and spinors in the quantum mechanics in very detail the first time. That's why we think the spins and spinors are quantum mechanical quantity. But the spinors and spins are actually classical quantity, fully relativistic. When you do the relativistic theory, Lorentz group analysis, the spin concept comes out naturally. And then, of course, we need to quantize it properly. That's when we learn things about the spins. What's a peculiar thing about the spinor is that spinors are not invariant under 2 pi 360-degree rotation. So this expression over here, exponential functions with the sigma over 2. Sigma is a Pauli matrices, angle is the theta vector is the angle. And there is a factor of 2, which is, this is needed because this guy needs to satisfy some commutation relationship. Because it is a factor of 2, actually you need to have 4 pi rotation to have a psi invariant. Otherwise, you need to have 2 psis to make the 2 pi invariant. If you have only one fermion, right, a psi, then you need to have a 4 pi rotation. So here's one example. Since I cannot show you physically, so I asked my daughter to illustrate this guy. So she's holding a cup. Look at the handle. Handle is pointing to the left on my screen. I hopefully it's not switched on your screen. So handle is pointing this way. So she's gonna rotate 360 degrees. See, 360 degrees. So pointing to the left again, right? The handle is pointing to the left. So 2 pi rotation. However, her arm is twisted. So this system is not the same as before, right? But then if she turns additional 2 pi rotation, she's gonna continue to rotate in the same direction. Again, then arm is untwisted. So this particular system, my daughter holding a cup, going through 4 pi rotation, actually this system comes back to the original state. So you can imagine the spinner as some kind of a vector scalar function which has an orientation vector attached to it. And so this is a completely classical, spinner is a classical quantity, right? And then, or you can imagine the spinner as some kind of vector quantity on the Mobius strip. Again, one of the mystery is why fermions are described by spinners. We don't know. I mean, that's I just wanted to mention that one. So that's one of the mystery which we need to answer. And the other thing that I wanted to mention to you about the standard model is actually the infinities. So infinities are everywhere, and then we need to take care of these guys. And then in the quantum field theory, which is the standard model is based on, this one has a very interesting way of taking care of infinity. So it looks like I'm going very slow. So I don't think I will give you a detailed explanation. So I think I'm going to skip. And then if you have any questions, you should ask Professor Figge, who is an expert on the taking care of these singularities in the complex calculations. I just wanted to make a mention that this singularity can be avoided by something called analytic continuation in the complex analysis. So it's fun to think about some relation between the zeta functions. Zeta function have something to do with the gamma functions, and the gamma function appears at the integral that I mentioned in the previous slide. So we see the gamma function every time, and then whenever gamma function has a negative argument, we get infinity. And then it's very interesting that this has some history related to the Ramanujan and Hardy and so on. So if you add all the integers, it's supposed to be infinity, but to use analytic continuation, you can actually show that some of the old integers actually turned out to be minus 1/12, believe it or not. So that's the power of the analytic continuation, which is actually one of the essence to eliminate infinity singularity in the quantum field theory. So the summary here on the standard model is we have a model which describes the particles, the interactions of in the fundamental particles, interactions of fundamental particles. So the standard model is 1 plus 3-dimensional renormalizable quantum field theory based on some gauge groups with the 3 generations of quarks, 3 generations of leptons, and 1 Higgs doublet. That's it's not, maybe I can add more, but this is a fairly accurate statement on the standard model. And standard model is more or less mathematically consistent theory, which means we know how to take care of infinities. And then it has been tested for a few decades, right? And then you know all these things very well. So the purpose of this plot is just to show the how well the theory, prediction, and experiments agree each other. And we don't have to look at the very details, but this one just shows the total cross-section measurements for the various processes. And then the circles represent the theory, the gray color represent the theory calculations, or other colors represent the data obtained from the LHC for different energies. So they within the uncertainty, they are actually in the very good agreement. And this agreement is over 14 order magnitude. So as far as I understand, the standard model is the only theory which works such a large range of the validity. Now, of course, this comes at the cost, right? I mean, we cannot do this kind of experiment and we cannot calculate things properly without using tools. I just talked about the mathematical tools, so-called quantum field theory, but to make a connection between the theory and experiment, of course, we need to do additional work, right? So all this complicated change, I don't mean to explain all the details, but it's not only the theory and experiments. To make a connection, to compare, we have to do extra work. So those kind of things are done by many people, including Professor Figge. And then I think I will let you to talk to him if you have any questions. Okay, so but nevertheless, standard model seems to be great, but nevertheless, we have so many questions. Like I said, why fermions fermions exist in the nature, why these guys are so peculiar. And then in addition to that, there are some physical questions that we like to answer. Where are all the particles? So all these kind of lists that you haven't seen them. I just wanted to mention one thing, and which is about coincidence and natural list and fine tuning. And this has been one of the main drivers to motivate looking for a new physics beyond standard model for last, I don't know, maybe 10, 20 years or so. This is a great guidance, but this is not the only guidance, right? Things right now, if you are following the literature, things become quite unnatural. I mean, going toward the unnatural direction, but that doesn't mean things are not unnatural, but we are kind of getting away from the sweet spot. For example, in terms of supersymmetry, supersymmetric particles become somewhat heavy, and there is some tension between the natural and then unnatural thing. But that's not the only motivation, right? This was a great driver, but we have all sorts of experimental evidences here. So these are the main drivers why we are pursuing new physics beyond standard model. Naturalist is just one of the theoretical arguments. And also, if you think about it, I don't know how many of you have seen this fossil. And I believe this is in the Sternberg Museum in Fort Hays in Kansas. And I think there is a big fossil, maybe 4 or 5 meter long fossil. And if you look at it carefully, there is another fossil inside. So it looks like a big fish ate small fish, and they kind of fossilized at the same time. And then this fossil happened to be in the middle of nowhere in Kansas. How likely is it? I mean, it did happen. What about this thing here? I'm pretty sure you have seen this basketball stuck on the rim, right? I mean, it looks like you can easily find this thing, right? It's unlikely thing. It's very unlikely to happen, but it did happen. So maybe it's not really natural to say unnatural things cannot happen, right? So I'm open to all the possibilities. To find these things, of course, we have to, once again, we need to have a model, we need the theory, but we need to perform experiment and then compare. We have probably many different experiments. And then I know that Wichita is participating in the Fermi experiment, the NOVA and the MINUBON, all this exciting neutrino experiment. Unfortunately, I'd like to focus on LHC today. Maybe I can talk about dark matter and neutrino experiment next time. But today, LHC, and then again, let me not give you all the details here, but you already know these things here. And then one thing I will say is it's big enough. And then I look at the map near the Wichita. So there are like a 135 and the 496. Actually, the LHC circle, right, ring, kind of fit in this closed loop, interestingly. And here is the Wichita State University. It's 17 miles the circumference. And then this LHC tunnel is 100 meter underground. And then there are several multi-purpose detectors. And then one of them that I'm interested in, 2 of them that I'm interested in is CMS and Atlas experiments. Basically, we do the collision. And using A equal to MC square, we want to create some new particles. So we look for the debris of the remnant or debris of the collisions to collect the evidence and then to predict something beyond the standard model and so on. Well, it's a complex experiment, right? We have several thousands of people working on this experiment, and then their detectors are very complex. And here's a tracking system, electromagnetic calorimeter, hadronic calorimeter, and muon chambers. So each part of the detector measures the different properties of the particles. And then once again, doing the analysis is actually very complex. Probably it gonna take at least a month or several years to understand certain subject. So this is not actually my expertise. I just know that this how complex this analysis is, how complex these experiments are. So to me, these LHC detectors are basically gigantic microscope. So if I want to see something small, I need to have a relevant standard, relevant reference, right? This is a reference, it will be a short wavelength. To have a short wavelength, or to Broglie wave, lambda is equal to h over p, I need a large momentum. Large momentum means a large energy. So basically, to see something small, I need an extremely large energy, and then take lots of photos, and then do the analysis, right? So I think these days, I think good cell phones have about 10 megapixel, roughly 9, 10, 11, 10 megapixel resolution. But I heard that the LHC detectors are 100 megapixel cameras and taking 40 million pictures per second. And this is a 4D, it's a 3D, and there is a timing information. It's a 4D pictures. 100 megapixel resolution, 40 million pictures per second. This is gigantic amount of the data is coming out. And it's too much, right? But it's a lot. So we have to actually choose some of the important the events to do the analysis. So that decision is a very hard decision. Which event we want to throw away? Which event we want to keep, because there's too much information coming out. It's unfortunately we have to throw them away. And then the detector generally has a kind of cylindrical shape. So if I cut the Z direction and then unroll, and I can have some kind of rectangular shape. And here phi is a azimuthal angle, and the eta is related to the polar angle. And then here the Z-axis is how much energy is deposited in the particular part of component of the detector. So higher tower means higher energy, more energy deposited in a particular location. And the different color represent different part of the detector, H-cal and E-cal and so on. So here the bottom line that I wanted to mention is that there are a lot of data coming out. And then I heard that now the LHC is going through upgrade, and hopefully they will be running next phase at the end of this year, early next year. And then there will be a lot of noise as well. So what is known as a pileup. So this a lot of collisions. We are not just looking at the collision of the two quarks. It's not a collision of the two protons, actually the collision of two beam bunches. In one beam, I think 10 to the 10, 10 to the 11th protons are there in each beam. These guys are colliding each other. There are a lot of noise, and then remnants are there. So how do we figure out what we want to look for here? So then that requires actually a lot of data analysis. And like I mentioned, there is a biggest problem is the amount of data coming out. And high luminosity LHC, actually the upgraded LHC will be gathering about exabyte within a few years of running, starting after upgrade. So exabyte is 1,000 times petabyte. Petabyte is even terabyte. My hard disk is only 1 terabyte. Right? So this is a lot of data is coming out compared to the amount of data Google has. I think this number was probably 3 or 4 years ago, 15 exabyte. But LHC will be gathering 1 exabyte by this per year by this time. So how do we store this one? How do we do the analysis? There is no way we can do everything we want. So we need to think about how we are going to process this amount of the data. This is not only by the experimentalist job, this is also a job that the theorist can jump in, because we need to be smarter in dealing with the data. That's where this the machine learning and AI ideas are coming in. So complex environment with lots of noise and lots of data coming out of the LHC collisions. So we need to think about how we can do the analysis more efficiently with the less amount of the resources. So hopefully machine learning could tell us a little bit better approach. And then, I mean, it's not new, machine learning. And then I'm not old enough to know all the history, but machine learning apparently always has been a part of the high energy physics, especially in terms of experimental analysis. So if you just typed, this keyword, machine learning and deep learning, artificial intelligence, neural network, these 4 just the keyword, no other variations. And then plot number of papers as a function of year, no accumulative per year. You see starting from early 80s, people were interested. I think probably some of the experimentalists who are very excited about this kind of neural network idea, probably they started using them early 80s. And then it gradually increases. And then there was a kind of peak. I don't know, this happened to coincide with the lab starting and the Topcock discovery. I guess they had exciting data. That's why they wanted to do a lot of analysis using neural network idea. It kind of went down a little bit, but it stayed there always. You see, there's always around 50 papers per year within the high energy physics with this keyword. Then starting from 5 years ago, it's kind of jumps up, right? This is due to some advancement in the computer science, as well as the price of GPU went down significantly. So a lot of the more complex network we were not able to run, now we can do it relatively quickly. Once again, this field it looks like this field is changing very rapidly. I cannot even keep up. And then a lot of algorithms have been used for the classification problem and the regression. But of course, in physics, high-net physics, we use clustering and algorithm all the time. Jet reconstruction algorithm is already machine learning algorithm. And the people started using the anomaly detection, or people started implementing symmetry-based convolutional neural network. For example, when you do the convolutional neural network on the sphere, somehow the data augmentation procedure has something to do with the Decays transformation in the field theory. So that's very exciting things. So after all, we are borrowing some of the ideas and tools from the computer science at the moment. But if you think about it, how particle physics actually developed in the past, at some point, we hope to provide feedback from particle physics side back to the computer science community, because we also have some knowledge accumulated. We can actually combine this, our knowledge and the existing tools, and then transfer this idea back to the computer science, hopefully in near future. So all this kind of idea is actually very simple. After all, I'm a theorist, so I'm more interested in how the machine learning thing works. But then if you follow the literature, I think it goes back to, I think probably most people will agree, it goes back to the paper by Kolmogorov, 1957. He was trying to develop some kind of approximation method. He was a great mathematician, statistician. So the way he was doing was a completely mathematical approximation. So he used a different phi function, but then later mathematician or computer scientist Sibenko, 89, he used something called I think tangent hyperbolic function, this exponential function here, that has a shape looks like this. And then computer science, people call this guy as a sigmoid function. But it's literally, I mean, this is a tangent hyperbolic function, right? It relates to tangent hyperbolic function. And this has been used even in the gravity, right? Penrose diagram, people use this kind of things to bring the infinite boundary to the compact space, right? That's what this function does. So what is interesting is that in this paper by Sibenko, 89, he used the exactly same one function, phi, and then make a linear combination and feed that as a part of the input of this function phi, and then make a linear combination of several of those guys, then you can approximate any function that you are interested in. So this is what is known as the universal approximation theorem. I know this sounds a little bit complicated, but it's very easy. Think about Fourier transformation. So f of x is the function that I want to approximate. If I want more precision, just include more terms. I mean, it's not perfect, but the statement is that if the function satisfies certain property, namely periodic property, then you can always approximate original function f of x by including certain number of sines and cosines. And then we can calculate the coefficients exactly. I don't need the infinite number of sines and cosines. And you pick the precision, you can always represent function f of x in terms of a trigonometric function within the precision. That's the approximation theorem I'm talking about here. In the previous slide, Sibenko used this one function called the sigmoid function. So this kind of approximation has been used everywhere, including physics and math and traditionally. Here is another example. Suppose I'm trying to approximate this function here that looks like a quartic distribution, right? This guy. Then I want to approximate this function by accumulating this little potential barrier, this guy. So that by having this little guy over here, like zigzag, 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 I can approximately represent this original function, smooth function. But I don't have to use the potential barrier. I can use this Gaussian distribution, or I can use this triangle shaped distribution. Basically, I can use any distribution, unit distribution that I want to approximate the original function. Right, here is a very specific example. Here is a cubic function. Then I'm going to introduce this guy, what is known as a ReLU function, rectified linear unit. This is nothing but this 0 when x is negative. This is just equal to x when x is positive. This is flat and then linear. It's a very simple function. I can even represent this cubic function, right? So here is the way we do it. So I'm going to introduce 6 functions, n1, n2, n3. All of them are written in terms of ReLU function. Of course, inside, this is a linear combination of a constant and then one-dimensional variable x. Then I make a linear combination of these n functions. I'm going to call this guy the big F. Original function is little f, which is a cubic function. You see that graphically, we are making the error, but it's not too big, right? They are close enough. If you want a better precision, you just include more n functions. So graphically, you can represent this way. Here is the input, here is the output. The output, big Y, is gonna be this big F, okay? Big F is the output vector, but I want this output to be as close as possible to this original function, little f. But then the way I'm gonna do is, we have six different functions. So I'm going to introduce 6 circles. Each circle has this ReLU function inside. And then this number here, -5, I draw a line, multiply by -5. This guy is gonna be the coefficient of the linear combination inside this function. -1.2 is the coefficient of the inside the linear combination here. I'm gonna write down this 6. And I'm going to make, as you know, we are gonna make a linear combination of these guys with some weight. In this case, it happened to be ±1. So basically this expression over here. So there is a graphical interpretation, graphical representation of this procedure. And this graphical representation is what is known as a neural network, naively. And then here, the important thing is the same function has been used throughout the entire discussion. And then, as you know, there are this kind of things can use the object classification. So you have seen this word many times, so I don't want to bother you, okay? And then what happened is that in this image over here, in the energy deposit in the calorimeter, actually can be used in some sense, the energy, the image in some sense, right? It's a flat, and then the higher energy means at the darker density, and the lower energy means at the lighter density. So the pattern, the energy, how much energy is deposited, has something to do with how dark that particular cell is. So we can actually do the image process the way the machine learning community has been doing. Different channels could represent the different particles. For example, I think for past 5 years or so, 2 to 3 years ago, people have been studying a lot of things about the top quark. How top quark is detected in the detector, and over the background, so-called the QCD jets. And again, the y-axis is the phi, azimuthal angle, and x-axis is the polar angle, so-called the rapidity and error. Here is the expression. So in this 2-dimensional space, and the left plot is the sort of a footprint of the top quark. Darker color meaning the higher energy, a lighter color means the lower energy. Same thing, QCD jets. This is supposed to be a background, supposed to be a signal. They look similar. They look different. Once again, it's very difficult to say because this is one particular event. However, if you accumulate many events and they overlay in the same plot, now you see there is some difference. So we can actually use this information to discriminate the top quark and then the backgrounds, whatever is detected in the detector. So the patterns are slightly different, but event by event, they look similar. So in principle, the similar idea can be used to discriminate so-called the light jet, UDS, U quark, down quark, strange quark, and the charm quark and the bottom quarks are a little bit long-lived. So their decay pattern is slightly different. Gluon has more QCD charges. So the QCD interaction is more complex than the other guys. That's why there are more particles coming out. Pileups are completely random. They do not originate to the one point. So the patterns are different. And W and then jet particles kind of considered to be the two-pronged jet, because W particle is not a fundamental particle. They will decay into jet. And Higgs particles are also more complex, top quark as well. So all these patterns are different, differently stored in the detector. And then maybe we can find something, some new patterns, which we don't know. There are a lot of ideas have been around already. So once again, I only know very little of these guys, but the point of this slide is there are lots of new ideas already applied to the discrimination of the jet. So what I want to talk today is something about Higgs. So why Higgs is interesting? We have discovered it. So what, right? But if you think about it, what we know is only the one term in the Higgs potential. So if you think about it, you have some general type of potential in the y-axis like this. And then what we do is we choose one of the local points and x star, and we do the expansion around the minimum point or local minimum. Then the first term is a constant, which doesn't matter in terms of f equal to ma. And then the next leading term is the slope. So if we do the expansion around the minimum points, of course, slope is 0. So this term is gone as well. So the very first non-trivial term is a quadratic term. And this is why we always look at the harmonic oscillator. And this appears everywhere in physics and tied with the Hooke's law. So Hooke's law is the very first non-trivial term in the expansion of the potential. Similarly, we can do exactly the same thing in the Higgs potential, and H is supposed to be Higgs field. There will be a quadratic term, there will be a cubic term, there will be a quartic term, and dot, dot, dot. There will be more terms. What we discovered so far is only the first term. So what that means is that we just know that there is some kind of minimum structure. We are in one of the local minima. We do not know what kind of shape the Higgs potential will follow. We need to measure the cubic term. We need to measure the quartic term. We need to measure the quintic term, and so on. So know the exact shape of the Higgs potential, we need to measure the high order terms. Otherwise, we do not know anything. What we know is only the near minimum point, which has something to do with the mass, has been measured 125 GeV. So to know the shape of this potential, we need to measure the next leading terms. So next leading term involves 3 Higgses, meaning that in terms of production at the LHC, this involves 3 Higgs particles, and then happen to be 2 Higgses in the final state. So when we do the proton-proton collision, we get 2 Higgses in the final state via another Higgs. So this Higgs in the middle is invisible. We get the 2 Higgses in the final state, but Higgs is an unstable particle. They will decay further into BB bar or some other particles. So it has, so then to understand why this is important, because by measuring the extra this coefficient, the cubic term and the quartic term, we can actually know the origin of the Higgs potential. Is it coming from the supersymmetric model? Is it coming from the extra dimension or composite Higgs model? Probably we want to have a very good precision on the C3 and C4 coefficient to tell these models, but in principle, that's why we are doing it, right? So like I said, the Higgs is an unstable particle, so they will decay. And this table summarizes how Higgs particles decay. And then these boxes are often the channels that people have studied. And then now what I'm interested in is a particular guy here. One of the Higgses decays into BB bar, pair of a bottom quark. The other Higgs decays into 2 Ws, and one of them is off-shell particles. And the Ws further decay. So I'm interested in actually the leptonic decay of the W. So in the final states, I'm expecting 2 big quarks and 2 leptons and some kind of missing particles because the neutrinos are produced in the final state. Surprisingly, you can count how many papers are written since Higgs discovery in this particular channel. Before my paper, there were 2 papers. And then both the papers actually said, no, this is one of the worst channel and they do not work on it. So that was very interesting because this final state happened to be exactly the same as the top quark final state, top quark production dilepton final state. So here's one of the paper 3 years ago, the Theorem group actually published this paper. Some postdocs published the paper. So what they do is they actually look at some of the kinematic distributions in the double X, and the dominant background is what is known as a top quark dilepton production. They look at the distributions. These guys individually, these guys are good discriminators. So then they run some machine learning algorithm called the BDT, boosted decision tree, and then they get the output, and these are their results. And here's the background numbers and the signal numbers. And then out of about 3,000 backgrounds, over 2,000 is the TT bar dilepton backgrounds. And the signal number of event is about 35. And the final significance is 0.6, for example. Here, the dominant background is again the TT bar dilepton channel, dilepton production. So it's very difficult to see. And then even here, we are not talking about any systematic uncertainty. Just purely statistical uncertainty is very bad. Now, this actually brought me a big question. Why are we choosing these variables, right? And then I can tell you more about these guys. That's another probably thing. But what's interesting is all of these variables, one at a time, they are great. They give a great discrimination power between the background and signal. But surprisingly, once we impose these cuts, so-called the missing ET, missing transverse momentum, rest of the cuts are less effective. Individually, they're effective. But once you import the first cut, second cut becomes less effective, third cut becomes less effective. Usually that's how it works. But the thing is, these particular variables here, except for masses, right? These angular variables are very strongly related. So these guys are individually great cuts, but these guys are very strongly related to each other. So when you feed this guy into the machine, actually all of these variables are not as effective as before, because you just need as well as input just one variable instead of 10 variables. So the understanding the data is the very first thing when you feed these guys into the machine learning. Machine does not know what these guys are. Machine will be working very hard to understand the discrimination between signal and background using these variables. But if you feed the wrong input, there is no point of the running machine learning. The very important thing is we need to understand the data first, and then we need to feed this guy into the right network structure. So like I said, if you are interested, I can tell you more about the details, but I just want to mention in this slide, in the signal, we have 2 big quarks, 2 leptons, and missing particles. Backgrounds, T bar is the majority, the dominant background, have exactly the same finite state. This is what is known as irreducible backgrounds. But topology is different, right? Look at the diagrams, the Feynman diagram, topologies are different. So using the different topologies, with my collaborators, I defined some kind of kinematic variables using kind of, you don't have to pay attention to the expression. This one is some kind of mass fit. In the top quark, we have 2 top quarks and the 2 Ws. So I'm going to use a mass constraint to figure out the momentum of the missing neutrinos. And I'm going to use the chi-square value as a part of my kinematic variable. And actually someone called toughness. I'm going to do exactly the same thing for the Higgs sector. I'm going to define some kind of a kinematic fit related to chi-square fits. And I'm going to call that variable as a Higgsness fit, because that has something to the Higgs property of the Higgs. Then the idea here is, once again, there are some details, but let me skip. Idea here is for each event, I can get the 2 numbers, toughness value and Higgsness value for signal, toughness value and Higgsness value for background. So y-axis is top-like, x-axis is Higgs-like. So for the signal, the fit should be better in terms of Higgsness. So signal is in the left side of this solid line as added as a reference. But the toughness should be bad. So the toughness value for the Higgs should be big. Higgsness for the signal should be small. It should be the other way around for the backgrounds. So all the backgrounds in the below this reference line. So basically, I was doing machine learning by hand because I was not smart enough to be able to run the neural network. So this is actually what is known as a so-called kernel method in the machine learning literature. So I was basically doing these things by hand myself. And then my colleague told me, oh, you guys are running machine learning. And then that's where I heard things about the machine learning neural network. That was 2 years ago. And then remember the jet images. So we did the same thing. And then, so in the first paper, in our PLL paper, we just used the conventional analysis. But then we just used this the linear fit, exponential fit. We just fit it by hand. Now we can feed this guy into the machine learning, let machine to figure out the best cuts. So in addition to the Higgsness and toughness, another improvement we thought was the images. So in the plot in the left are the images of the double Higgs. The plot in the right, images of the top quark production. So the upper plots are the energy deposits coming from charged particles. And the lower 2 plots are the energy deposits coming from neutral particles, which means that there is no track associated with the 2 plots. And then the top plots, we look at electromagnetic calorimeter, hadronic calorimeter, and then the energy deposit is associated. And then we have 2 different images for signal and then background. And then if you sum of all particles, you remember the error phi space images are different statistically. Event by event, they look similar, but statistically, they look different. Now we feed this guy into so-called the convolutional neural network. This is not something that we have invented. People have been using it. So we just borrowed the tool. This is a very popular tool in the past, and we just borrowed a similar structure and then feed our images into the network. But we also have kinematic variables. Remember the 10 variables that used by the previous group. And then I proposed the 6 additional mass variables that I call high-level variables, because these guys are always related to masses. Personally, I like masses over the angles, because angles are not invariant quantities. Masses are invariant quantities over the NLO or this boost. So I prefer to use the angles over the masses over the angles. So then we fed 2 images into the network via convolutional network, and the regular DNN structure added for the 2 sets of the different kinematic variables. We combine the score and then use the common, the cross entropy score. So basically at the end, we get a score. And then the x-axis here is the score, and the y-axis is the unit normalized distributions. So by construction, the signal is supposed to peak near the 1. All the backgrounds are supposed to peak near 0. But most of these variables are designed to kill the θ backgrounds. That's why θ peaks much higher than the rest of the backgrounds. But all the other backgrounds are kind of flat, although some pink, for example, TW, there is a top in it. That's why this one also peaks in the lower value. So what we do is we use the P1 score, a neural network score, as our kinematic variable. So we cut, and we can count how many events are past the cut. And then we can improve our significance a little over what the CMS group did 5 years ago, 4 or 5 years ago. So there was a high Lumi projection study done by CMS group. They were proposing 0.6, but we are actually getting at least a few times, twice better than significance they ever proposed. So what I'm doing recently is actually follow-up study. So in the left 2 plots are the ones that we have used in the previous results. But then actually these are 2 plots obtained from the hadronic calorimeter, the image of the hadronic calorimeter for the charged hadrons and neutral hadrons. But we can actually look at the electromagnetic calorimeters, namely photons and the leptons. So if you accumulate, if you stack all the events in one plot, so these are the patterns. You see these patterns are different, right? I mean, important thing is patterns are different. Can we use that to discriminate? I mean, we are using that in terms of kinematic variables, but maybe we are missing some of the information which existed there. So we want to feed these images along with the kinematic variables so that we can learn a little bit more. And what's new in these 2 plots here in the right side is that as a part of the minimization procedure that I proposed for the toughness and thickness, this method actually tell us approximate momentum of the missing neutrinos. So one of the biggest obstacle in the hadron collider experiment is when you have a missing transversal momentum, we don't know how many missing particles exist. We don't even know that they're individual XY momentum or Z momentum. So missing particles, we are literally missing the momentum information. Now, this method actually tells us approximate neutrino moment. They are not perfect, they are only approximate. But nevertheless, you see that this between the signal and the background, these patterns are different. So in fact, the neutrino image should be similar to the lepton images. Actually, they are similar, right? If you look at these 2, they are similar. Even for the background, their images are supposed to be similar. They are similar, I mean, not identical, but between signal and the background, they are different. Can we use these patterns in the missing transverse momentum obtained approximately as a result of the kinematic reconstruction? Yes, we can. And that's what we have been doing. Unfortunately, this image is actually 6 different images. And then our convolutional neural network actually did not give us a significant improvement. And we were told by computer science colleague, there is a little bit improved version of convolutional neural network called ResNet. I think I forget which group, Google or some other groups actually won the competition in the past, what is known as ResNet 50. We look at the data structure, we kind of modify the data structure for our purpose. So at the end of the day, feeding the 6 images, here this plot in the left bottom corner shows the significance for the θ background only, not including all other background, only θ, because the goal was to kill the θ backgrounds. And this was the result that we were getting before with the 2 images, including photon, but including the lepton images, we can improve further. And including neutrino images, we can improve even further. So black curve is this sort of our final result. And once again, you have to be a little bit careful. This significance is not actually true significance because we are including only theta background. There are other backgrounds. This number actually will go down, probably 1.5 or so. This guy will go down by a factor of 2 or so. But I just wanted to illustrate the improvement upon the previous analysis over the convolutional network and the ResNet and over 2 images and the 6 images. So there's an improvement that we can make. So this is something that we are working on. So important thing is we want to make sure that we are not overtraining. So there are some subtleties and so on. So that's something that we are checking at the moment. Well, so I guess my time is almost up. So I think I will try to wrap it up. So we are looking for many exciting things, and the Higgs was one of the examples, which is actually guaranteed at the high luminosity LHC. And there is a lot of exciting opportunities using machine learning to improve discovery of this cubic coupling in the Higgs potential. But there are other things we are looking for, right? Well, I think probably some of you might remember this explanation by Professor Shipsey in the past. Think about what we are doing, right? We are looking for something. We want to find something that we did not know before. Hopefully that gives us some explanation to some of the puzzles that we have. Whatever we are finding at the LHC, right? Basically, this is our understanding of the universe. We'd like to improve. So this perception, our understanding of the universe, perception is a dynamic combination of a top-down and bottom-up approach, a theory and experiment. So here he gave a very nice illustration. So if I tell you what would be this is a photo of somebody who is very famous in the history, right? I'm sure probably you already guessed who this person might be. So we don't have a lot of data, so resolution is very poor. So maybe you may not be able to guess, but you have some idea. I already told you this is a person. Now we get more data from here to there, getting better. More data, getting better. Whenever we get more data, you feel more confident about your inference. When you get more data, then you feel very confident. You get more data, right? Then finally you confirm. So this is a dynamic combination of the top-down and the bottom-up approach. However, let's look at another example. Once again, this all credit should go to the Professor Shipsey, and this is actually a great illustration to tell us where we are. Now, I'm not going to tell you anything. We don't know what this photo is. And then we have to figure out what this picture tells us. So our data is very poor. We don't even know what we are looking at. And getting more data doesn't help. There is more data, doesn't help, right? Getting more data doesn't help. More data, even more data doesn't help. And then, as you know, this is the famous paintings of the Dali, a very abstract. I forget the name of this style, but this is a very complicated drawing or art. We cannot even understand because we don't understand the meaning. And then even with this, a lot of data coming in, it's very difficult to understand what it is. So basically what we are saying over here is that since Higgs discovery, somehow we are in a situation, we are trying to recognize the Dali's art with very little information guiding us. So without the roadmap, we are highly dependent on bottom-up approach, basically experimental input. So in that sense, we are in a data-driven era. However, I should emphasize that even the data-driven era, theoretical inputs are very crucial, very important. And I hope that the machine learning could kind of provide the potential help to resolve this situation. And then, of course, this machine learning, all these things that come from the tech industry, computer science. But in some sense, we are doing the same thing. Although, I mean, as I said over here, the Amazon, for these companies, are not actually interested in very small number of customer behavior, but we are interested in that in high energy physics. So I think I'm going to stop because my time's up, and let me conclude. Standard model has been very successful explaining the data, but it still has a lot of open questions. And we are expecting a lot of exciting experiment coming up and the ongoing experiment looking for new physics standard model. And then one issue is the complexity of the experimental data requires efficient method for the data analysis. Like I mentioned, like a lot of data and then noises. And then hopefully this machine learning in the idea actually can help us in this situation. And then of course, the computer science fields, there are lots of advancements, and we can borrow some of the tools. And then in the long run, we hope to provide our input to the computer science back to the community. And then I just want to mention that a lot of data and the interesting data analysis will lead to the new discovery. Okay, thank you for your attention, and I'm open for the questions.
Are there any questions?
I could ask one, Terrence.
Please.
Go ahead.
So if you have this, it looks like it's kind of slow for artificial intelligence. Is it just my impression that it's a slow process, or is it really fast?
What do you mean by slow?
Well, I mean, I just have the impression that the time consumption of doing these computing and learning might not be applicable to artificial intelligence for, say, driving a self-driving car.
Oh, actually, I'm the wrong person to answer the question. But I mean, in terms of advancements, I don't know. So we have one faculty in the engineering, EECS, Brian McClendon. I don't know whether you know him. So he was a Google Earth guy. So he made this Google Earth engine. He made this company in the Silicon Valley after he got a master's degree from KU. And he sold basically his company to Google, and he was hired by Google. He was the one who made this Google Earth. And then, believe it or not, that they are the first team in the Google who started this Google Earth, right? When you take a photo, I mean, Google has lots of almost infinite amount of data, right? A bunch of photos, right? You remember the Google car going around the road and taking lots of photos? There is no way for human to tag their address and then associate with the location and images, right? They had to make this everything automatized. So there was an intern who actually gave an idea, and then that was great. And they started actually using this machine learning very heavily. That's what he told. And then 10 years later, 15 years later, he moved to Uber company in Pittsburgh. He was working for autonomous car, as you said. But he actually believes that in the Kansas City, within 10, 15 years, a lot of car will be gone, private car will be gone, and the autonomous car will be running on the road. I'm not sure how fast it can come, but he said he's very confident. So, but as you know, I'm the wrong person to answer that question. But of course, a lot of work needs to be done. And the one question that I asked him was, why don't the autonomous cars just communicate each other, right? If there are so many autonomous cars actually going around in town, and then one car in front of me can pass the information to the car coming behind. That way, this second car coming in can be prepared. You know what his answer was? That's a great idea, but we don't have time to think about it. Because getting the input from the car, the environment is constantly changing. And then getting that information, digesting that information, and make a decision, that's the most important thing for them. Communicating between the car is a secondary.
Yeah, that information already exists. I think that all cars by the year 2025 are supposed to have these transponders that could tell other cars what's going on. And my Ford C-Max Energy, which is a battery car, actually, when I get close to a Tesla, it tells me information about which direction it's heading and what speed it's heading. Mm-hmm. On the road. So some of that information is already being transmitted between cars. Mm-hmm. But yeah, it'll be a long time before they're all equipped.
Yeah, so I to be honest, I don't know. But to me, I mean, these kind of tools are amazing because I mean, this improvement that we are making is not factor 2, right? It's not factor 3. It's a 10%. Sometimes if we are lucky, maybe 50%. But it's not gonna be factor 2. If we get a factor 2 enhancement, certainly by switching tool one from the other, that means we must have been doing something wrong before. So, but nevertheless, these tools are amazing, and then we can learn something useful out of it. So that's what I'm hoping for.
Okay, thank you.
I have a question.
Yes.
Richard Traverso. You mentioned there's a sort of connection between some of these machine learning algorithms and gauge transformations. I mean, these are the gauge transformations on typical Lie groups, or can you comment
yeah, that's what I
general?
thought. Essentially, yeah. So I think I once again I should say I don't know the full detail. I just read the paper very quickly. So I think these people are interested in you remember when you do the image processing, there is apparent symmetry, right? So what people do is they do the pre-processing via translation and rotation. This is such an obvious thing, so that the neural network doesn't spend time to do the analysis. We already do the data processing to begin with. But what these guys are doing was some kind of image processing on the sphere. The sphere has some kind of symmetry, basically rotational symmetry on the sphere. So this guy has something to do with the gauge transformation we do in the gauge transformation we do in the field theory. But it's not one-to-one though, because this is such a simple example, but mathematically they were related. And when they write a paper, they were kind of a little bit exaggerating, right? It's a symmetry argument, the data pre-processing, but that was related to the gauge transformation in the field theory, because the theorists were involved, helping the computer scientists doing the convolutional analysis on the sphere. That's how they just wanted to make a connection. But it's not the gauge transformation we do in the field theory though. But mathematically it's the same thing, but it's not the same gauge transformation.
Okay, yeah, that's what I was wondering. Thank you.
Yeah, thank you. So all this pandemic time gave an opportunity to play with the robot thing. And I was learning some of the algorithm. I think this was something called the Q-learning algorithm. And there were two motors there. And then this one robot doesn't know anything. These two motors are moved randomly. And then to move forward, right, you have to stick this guy underneath of the motor and then push forward. And there is an ultrasonic sensor which measures the distance. And now this is completely random. So it's not learning anything. So then it gets a penalty. Then when this guy moves forward, it remembers past a few movements and then try to do something similar based on the previous learning. And this guy will go underneath kind of accidentally and then move, push, and then moves. Then distance gets reduced. Then now it remembers a few past movements. So then it's gonna remember. Next time it's faster. So then if this learning was done over like an hour or so, then it's okay. I mean, so this was very interesting. I hope maybe we can learn something from these tools for the particle physics too. Any other comments and questions?
It looks like we don't have any other questions. Yeah, I want to thank you for giving that talk. It was really good. Thank you.
Thank you.
Yeah, thank you very much for a nice talk. So next time we have the next talk a week from today, Abhishek Kumar from the Marine Biological Laboratory will be talking about leveraging computer vision with advanced optical imaging. So join us again next week, and thank you, Casey, for a very nice talk.
That sounds great. So yeah, let me try to come back next week, hopefully.
Sounds good.
Yeah, great. Thank you.
Right.